Okay, so we're going to talk about polarization for a little while. And I just handed out a bunch of linear polarizers we'll use in a minute. This afternoon, we're gonna have the lab on polarization. Just go ahead and keep the linear polarizers that you've got during that lab, but then return it after the lab somewhere. We'll say we're gonna put them, I don't know, somewhere in the lab room, if you can bring all that. But you can keep it until then, because you'll use it this afternoon. So why does it do this? There it is, okay. Polarization is light, it's important. It's another parameter of the light field you can measure. You may be able to get some more additional information about the particles that are perhaps scattering light. In any way, it's another part of the light field that we can measure. If you remember what light is, basically, it's an electromagnetic wave. You can describe it as just a plane wave. Either it'll have an electric field going in one direction, electric field could be going in another direction. If we look, let me get out of here and do something more fun. Escape. How do I escape? And show. Okay, let's check this out. Can you see this? Yeah. So this is sort of, will show you the effect of the dot is the vector sum of having an electric field along the x direction or electric field along the y direction. So let's look at some examples. I can set, if you copy down this link, you can look at it yourself later for fun. If I set Ex, the electric field on the x direction is being this factor of 8, and put electric field of 0 on the y direction, and watch what happens as electric field goes by one point. Basically, it's just oscillating in one direction back and forth like this. Okay, so that's linear polarization. It's all the electric fields occurring in just one plane. Similarly, I could have it instead of the x direction. There's no reason to not have it in the y direction. So I could put 0 for Ex and 8 for Ey, and you would see it just oscillating up and down like this, right? What happens if I put it, I'm going to put 8 in both. Have 0 there. Okay, what do you think what's that going to do? So there's no phase shift between the x and the y, but there's 8 in both. So what's it going to do? Okay, let's work an equation. If you look back at my thing here, phase shift is 0. Let's say we're just looking in time, you get the same amplitude there. So as time goes by, this go up, this cosine of omega t, this is going to go up cosine of t. So what's it going to do? It'll just go up and down like this, right? They're both be synchronous, so it's going to be, as one goes up this way, it'll go up that way, and then go that way. So it's going to be at a plane of 45 degrees. So let's look at that. So I'll start it. Oh, I didn't set, I forgot. I had a really nice program that did this, but so you can see the x going up, the y is going up, and so it's going to be oscillating at 45 degrees. All right. So now, that's all. These are all examples of linear polarization, meaning the polarization, the light field, the electromagnetic vectors are always propagating in one plane. The plane defining by the direction it's propagating and the way the electric field is oscillating. Okay. So this is an example of linear polarization. Now, I can stop that and introduce a phase shift between the x and the y. All right, so let's try a phase shift of 1.5 radians. Remember what a radian is? Anybody remember what a radian is? Remember degrees? Okay. Degrees, there's in a full circle, there's how many degrees? 360. Okay, radians is a measure of angle too, right? So what's a full circle in radians? 2 pi. 2 pi radians going around. Okay, and so 2 pi is a value of about what? About 6 or so. Pi is about 3, is a little bit more than 3, so about 6. So if I go 1.5 radians, how many degrees is that probably? About 90 degrees, okay? Because 3 is 180, or 360 is 6, somewhere a little bit more than 6. And so 1.5 is going to be about 90, a quarter of that. So let's watch what happens to the light field, to the electric vector, if you set the x and the y just out of phase by that 90 degrees. So let's see, I set the values, I do it right this time, and we'll see what happens. So notice what's happening is because they're out of phase with each other. When one's the minimum, the other one's going to be maximum, and vice versa. So you have the electric field, the tip of the electric field vector continually circling around like that. So that's called circular polarized light. And you can have left circularly polarized light, or you can have right circularly polarized light, depending on whether the electric field is going like this, or going like that as you go off, okay? So those are, in general, those are the pure polarization things, would be linear polarization along some plane, and right circular polarized and left circular polarized. Now, you have, I handed out linear polarizers. Let's play with those for a second here. A linear polarizer is something that just lets one plane polarization through. You can tell what the acceptance of the plane polarizer is by looking at a surface with glare on it. So say we're looking, can everybody see someplace on the floor that's got a sort of bright glare coming at? Everybody got that? So if you rotate the polarizer, looking at that, you should see the glare be brighter or darker. Okay, do you have the polarizer? Oh, you didn't get one? Anybody, any answer on that? There's 2 everywhere. Right. Sorry, I didn't realize that it did all the way around. Okay, so everybody, if you look at the floor and you look at a glare spot on the floor, and you rotate it, you see where it's bright and where it's dark? When you look at a surface like this, light preferentially reflects polarized light horizontally, okay? So if you have the polarizer such as the acceptance plane is vertical, you're going to knock out that glare. So by doing this, whenever you pick up a polarizer, you can rotate it in like that, and look at a piece, some glare on the floor or something like that, rotate it, and you can determine where the acceptance is. Okay, so if it's dark, it means that you've now got this way. So everybody know which direction their polarizers are now? Okay, so the next thing we're going to do is you're going to work with your neighbor. And so rotate, since we don't have 3 polarizers per person, we have 2 polarizers. Work with the person sitting next to you and rotate the 2 polarizers relative to each other. So let's see what happens. What's that? Well, just see what happens when you rotate it. On top of each other, yeah. What's that? There's no glare. There's no glare left. As we rotate, what happens?
No glare.
And no more rules either, right?
Yeah.
Yeah. So as you rotate the 2 polarizers on top of each other, at one point you're going to have no light going through the combination, right? Because the first polarizer is only let light come, say, this direction. I don't know which way you had yours. This direction. And the next one, it at some point would only let light coming horizontally. And so now all light coming is vertical, there's no light horizontal, so there's no light through the system. All right, so cross polarizers that let no light through it. The way those polarizers are all built effectively is they've taken a plastic sheet with long molecules and they sort of stretch it so all the molecules are lined up in one direction. And so if you think about the electric field going through there, it's very easy for the light to be absorbed if the electric field is going along the direction of that chain, long-chain molecule. If it's going perpendicular to it, then it's not very easy for the electrons to absorb that energy in the molecule. So basically, it lets, if the molecules are aligned like this, it lets light go through this oscillating in this plane. Blocks, absorbs the light oscillating in this plane and lets light through oscillating in that plane.
So when they're on top of each other, one is going this way, one is going.
When you have them blocked off, then the two acceptances are perpendicular to each other. I don't know which way you have yours landing.
It's a little counterintuitive, right? Because you have molecules going through like the light going through like this.
You would say, yeah, but it's perpendicular. It's perpendicular.
And it also stops the circularly. It also stops circularly polarized.
If you think about circularly polarized light, what's going on there is that you've got light polarized in this direction, light polarized in that direction, but they're just out of phase. So it's a linear polarizer is just going to let one of them through. So you can get half as much light coming through in that case. Now I need to do 3 polarizers. So 3 people together. Okay, what I want you to do is cross 2 of the polarizers, but before let's think about this first. I'm going to want you to cross 2 of the polarizers and then stick the third person's polarizer in between the 2. What do you think is going to happen? Think you'll get a lot of light through? Think you'll get no light through? Think you'll get no light through? Okay, so here's one. How many people think no light? Okay. How about lots of light? Lots of light. How about medium amount of light? Okay. All right, so let's go ahead and try it. I want you to do is cross the 2 polarizers, the outside polarizers, and then rotate the inside polarizer and tell me what you see. It's sort of, it may take 2 people holding it at least.
You want one to be out of phase. Okay, now put this one back in.
Everybody had a chance to see it yet?
So that's this, and then another direction.
Okay. All right, so everybody had a chance to look at it? No? No. This maybe should have been part of the lab. Except this way I get to explain it all at once instead of 5 different times. Okay, so what did you see basically? You have the cross and you put the other polarizer in there. What happened? You see light, but light, they were crossed, you had no light.
Right, and then you
put it in, you get some light through. As you rotate it, what happens to it? Do you ever get a case again that there's no light coming through?
Yeah.
If you rotated it, if we think about it, if you have a polarizer, so it's accepting light looking in this direction, right? And now I put a polarizer that's oriented this way. Now, this one will let the light that's polarized in this plane through, Well, this can be considered some of this and, well, I'm sorry, some of this and some of that, right? And so basically you had the light polarized like this, I put it here. Now I let basically half the light through because half was polarized in this direction. And now the next polarizer is polarized like that. Well, once again, you have about half that can get through. But if I take the cross polarizers and I put the second one lined up with the first polarizer, what's going to happen to the light then? So I have this polarizer, it's let light through like this. I have another polarizer, it's like its acceptance is in this plane. What's going to happen? All the light should come through, but it's all going to be polarized in this direction. Now when the next polarizer is this direction, what happens? You get no light. Similarly, if I have light polarized in this direction, and I orient my middle one in perpendicular, what happens? You get no light again. So what you'll see if you rotated and knew all your polarization planes is the middle one would have, if it's lined up, if the two outside ones are like this, put the middle one like that, you're not getting any light. You rotate it, you get maximum light at 45 degrees, and you get 0 light again. Okay? But you get light through. One of the, we'll see if I can find some plastic during the lab this afternoon, and you can try, if you take a piece of plastic and stress it, maybe with plastic wrap you might do it. If you stress it and put it between polarizers, cross polarizers, the plastic will depolarize along stress lines. In fact, they used to build to test how building stresses would work. They would make a plexiglass model of a building, look at it between cross polarizers, and as you stress the building, the stress lines would show up, whatever you've constructed. Anyway, it's sort of interesting. Let's go back to the math, though. Okay, so this is basically the equation for electric field on the L direction, the R direction, and what's important is the phase shift between them. Phase shift is 0, the light's going to be linear polarized. Pi over 2, as we saw, is circular polarized. Now, in general, we can't really measure those electric fields because the frequencies are on the order of 10 to the 14th hertz. So what we look at is the intensities of the light, and so and the averages. So basically, what we're looking at is the average of the light polarized. Or well, let me go back. Let me think for a second here. So we can't measure the individual electric fields. So what we want to do is have a way that we can describe the polarization of the light field that doesn't depend on just the understanding and measuring the exact electric wave and all those parts. So what we do is we measure it in terms of the Stokes vectors. And the Stokes vectors are measured basically by measuring the intensity of light polarized in one direction versus another direction. So the reference system is basically for the I, if there's four components of the Stokes vector, the first one is the total intensity. So basically you measure the light that's polarized in the L, say, minus the light polarized in the R plane. Intensity is what you've been measuring up until now, effectively. The Q of the Stokes vector is the difference between the light that's polarized in the L direction minus the light that's polarized in the R direction. If you get unpolarized light, you can think of it having an equal amount of L and R, and so the Q would be 0. If it's all polarized in this direction, say this is your L frame, your frame, then you get a Q of 1. If it's all polarized in this direction, you get a Q of -1. Okay? Then U is the same idea, but now it's the light polarized at 45 degrees minus the light polarized at -45 degrees. Okay, so these Q and U are linear polarization terms, and then V is a polarization that's right circularly polarized light minus left circularly polarized light. If we look at some example Stokes vectors, Some simple ones, unpolarized light, you have an equal amount, you can think of it as an equal amount of L and R, or equal amount of 45 and minus 45, equal amount of bright and less circular polarized. It basically just has an intensity, and then the other Stokes vectors are zero, Stokes vector components are zero. So this is an example of what unpolarized light looks like. If it's polarized along L, it'll be 1, 1, 0, 0. Polarized along R, 1, minus 1, 0, 0. And then right circularly polarized light would be 1, 0, 0, 1. So B would be the non-zero element. Okay, so that's what a Stokes vector looks like. And we can describe the full polarization of the light field if you view these Stokes vectors. This is just to define a couple terms that I might show later. Mostly the degree of polarization is the sum of the square root of the sum of the square of Q, U, and V over I, telling you how much the light field is polarized. It ranges from 0 for totally unpolarized light to 1 if it was fully polarized. And then this plane of polarization, U over Q, tells you if you have a linearly polarized component, what angle that plane is in. Okay? So those are two factors that I'll talk about for a little bit. Ellipticity is basically how much of the light field is circularly polarized versus, how much the light field is circularly polarized is for that. I've gotten out of whatever. You guys can see it. For Stokes vectors to transform a scattering process or any kind of working on the light field, the process can be described by this 4x4 matrix, which is a Mueller matrix, called a Mueller matrix, and it describes how incoming Stokes vector becomes the outgoing Stokes vector. So if you have a scattering event and you know the Mueller matrix, you can describe how light polarized in any direction coming in, what it will look like when it comes out of the process. Everybody, how to describe? How many people remember how to multiply matrices? How many people don't remember? Okay, a couple. Just to be clear, the way you use this, how matrix multiplication works, is I would take I and multiply it by M11 Q, multiply it by M12 U, M13 V, M14, add up all that, and that becomes the new I. Similarly, I take I times 2, 1, Q times 2, 2, U times there, V times here, and sum them, that would be Q. So the way the multiplication works is sort of from here, going like that, and going across to that side. So if you know the Mueller matrix, you know how everything about the scattering process effectively. Example Mueller matrix, this is for a linear polarizer where for a angle theta arbitrary of what the angle of the polarizer is relative to some reference. And so that's in general what it is. Let's see what I've got here. If you start with incoming light in just arbitrary state, and I set up the polarizer so that theta is equal to 0, so I'll get a 1, 1, 0, 1, 1, 0, because the sine of 2 theta is 0, 0, 0, 0 for that third row, zeros. If I take this arbitrary Stokes vector, multiply it in here, I'm going to get I times 1, Q times 1, so I plus Q, half, you get half I plus Q. Doing the next row, I, Q, so I plus Q. The next row, there's zeros, so it's all 0 and 0. And so if you take the I plus Q out of it, you have a Stokes vector that's 1, 1, 0, 0, which is what, so this is a linear polarizer. It took any kind of light coming in and made it linearly polarized. That makes sense?
How would you ever get the Mueller matrix for like the natural environment?
So I'll explain that later.
So is it always symmetric along the end, or is that all the
Is it always symmetric around the diagonal? I'm trying to think of always.
In general, completely general, it's not. In the real world where we deal in, it's usually going to be.
Yeah, okay, so there, thank you, that's, I was trying to think that. Same thing.
When you're breaking it down to the four components and you add addition L and R, do those directions have to be completely perpendicular to each other or can you measure?
No, it should be, there should be a perpendicular to each other. And I didn't really go over it too much. In fact, I didn't say it at all. One reference, you have to define this reference with however you want to define it. In the natural light, what we tend to do is if you're looking at skylight, you think of the sun as, or where the light ray is coming, say, is light rays coming down like this, and the zenith, you have a plane that's formed between those two vectors, right? Coming like this and looking up, well, okay, light going out like that and looking up like that, there's a plane formed in my body, right? So that plane, we define the L to be parallel to that plane and the R to be perpendicular to that plane. Similarly, if you have a scattering event, that's light coming in, scattered off in some direction, that'll define a plane, so you have a parallel and a perpendicular to that plane. Yeah.
And then the light ray comes to a Z.
So light ray, the direction the light ray is going is. Okay. Anything else? Good. Okay, so we had this. I showed you how polarizers work. If you look at cross polarizers, you have the matrix for the one we just did. The matrix for a polarizer at 90 degrees would be 1, 1, minus 1, minus 1. So you start with this unpolarized light, in this case. You multiply it by this first Mueller matrix. You end up with 1 II 0, 0. Okay. You multiply it by the next one, so you can get I times 1, I times minus 1. Add those together. What do you get? 0. So basically, you're going to get 0, 0, 0, 0. Okay, so you have no light through when they're cross-polarized visors. If I put another one in between at 45 degrees, now the Mueller matrix looks like this. And I have, after the first polarizer, the light coming in is polarized in the L direction. I multiply it times this. What are you going to get? You're going to get I, and then 0, and then 0, so it's going to be an I up here. The next row is going to be zeros. The next row will give you an I, 0, and there's a 0 here. So you end up with 1, 0, 1, 0. Okay, so there is some light coming through. And now you multiply it by this, the next one, which is the cross polarizer, the last of our 3 polarizers. And you'll get, I think I actually have this on the next slide. Yeah. So we got the 1, 0, 1. We multiply it by this Mueller matrix, which was the acceptance being, say, horizontal. And you'll get 1, minus 1, 0, 0. So 1, minus 1, 0. But now there's a factor instead of a 1/4 or 1/2, there's an 1/8. So you get less light through, but you did get light through when you had the 3 polarizers. So you sort of see how these Mueller matrices work and how to work with them. Where, yeah.
What's the negative intensity?
The negative, remember when you had the Mueller matrix, this is the Q. It's I, Q, U, and V. So this is the Q element.
Okay.
And Q was the amount of light polarized parallel minus the light amount of light parallel polarized perpendicular. So minus means that it's all polarized perpendicular. And that's the amount of light. Okay. Circular polarized light. How do you make something? Yeah.
We get the light in
Uh-huh.
Because it's,
Okay, but in the previous one, so let's see. On this row, I had this one that was polarized. Now, after the first polarizer, it's polarized in the parallel direction, so it's a constant one. Okay, and in our example that I've been doing with my finger, it's like this direction. The next polarizer is polarized at 45 degrees. So light coming out of there is going to be has a 1, 0, 1, 0 because it's all polarized 45 degrees. And then it gets acted on by our last polarizer. And by the time it gets done with that last polarizer, this one now only accepts light. Let's light go through this polarized. Okay, so now it's all polarized that direction. Is this clear at all? Okay. Circular polarizer, the way you make a circular polarizer is you have to get the two directions out of phase with each other. So what we need is a quarter wave plate. And so you take unpolarized light, say, put it into a polarizer that's at 45 degrees, which is this Mueller matrix, and then you multiply it by the Mueller matrix for a quarter wave plate, which puts one direction of 90 degrees out of phase with the other direction, okay, quarter wave. And so that's represented by here. And here to answer to your question, are they always symmetric? So even a simple quarter wave plate isn't symmetric. So if you look through there, what you end up with is this one showing that it's all polarized in the 45-degree plane. You multiply it by here, and by having this element down here multiplied by that, you end up with a circular polarization component. So a circular polarizer is made up by a linear polarizer then a quarter wave plate. Interestingly enough, you turn that around, okay, and what are you going to have out of it? Nothing. If you start with unpolarized light, you're going to start with an unpolarized light and then multiply it by this matrix here, and all you're going to end up with is unpolarized light again. But then it'll go into a polarizer and become linearly polarized. So a circular polarizer depends on which way you face it, what it's going to do.
Is the quarter wave plate just like slow down light?
Its index of refraction is different in one plane direction versus the other. So it slows, well,
By a tiny bit.
yeah, one direction goes through faster than the other direction. Yeah.
Can you go through the terms in that quarter wave plate matrix?
Did I describe why it looks exactly like that? I didn't have a general, I don't have a general formula down.
For the minus one, right here.
Okay, so we have, okay. What this element is basically doing is taking whatever V down, whatever you have in terms of U in your Stokes vector and moving it into the circular polarization part, P. Okay. A minus one here means that if you had light that came into this that had a circular polarization component, it would end up giving you a U component when you're done. I can't tell you, I don't have the general formula written down for.
Sir, this was, it might seem really opaque for you right now, but this is really one of the frontiers in remote sensing of the ocean. Phase is going to have two polarizers. They're not two polarizers. One watches in multiple angle, the other one has more resolution in spectral, and there's really hope that we can learn much more in terms of information content. This is going to bring new information into our inversions about composition, about size of particle emission. So any one of you that's get into this, you have a wide open field to do wonderful discoveries. It's really a source of information that is not tapped as a community much today.
Okay. Right, so the next, now somebody asked, how do you get the Mueller matrix? Okay, so to determine the Stokes vectors, you basically, it's a 4-element thing. You need 4 different polarization measurements of the light field, and you combine them in different ways. And you can get what the IQ, U, and V. You can think about it, if you have one measurement that is polarizer this direction, one measurement is polarizer this direction, so how much light comes through. Put another one at 45 degrees, that's 3. And then if you have to have a right or left circular polarized analyzing. So those 4, you can get what the Stokes vector is. To get the Mueller matrix, what you have to do is have 16 different measurements. You have to measure, put in a known polarization state and measure what the Stokes vector is coming out. Put in another one, and the same thing. So you need 16 combinations to get the Mueller matrix out. Okay. And we typically normalize. I like having the normalization by M11, so it lets you see what's going on in the rest of the elements. When you're looking at a paper, a lot of other people don't like to do that, and then it confuses me because it's sort of like how much of this is real polarization and how much is just the intensity. This M11 element is basically the phase function that you've been doing from the scattering. Okay. And so now I'm going to go through how some of the instrumentation for you do. Yeah.
You're saying how much is the intensity? The intensity will change all of the values in the Mueller matrix? If you don't normalize to M11.
Oh, if I normalize to M11, the rest of these elements, everything's divided by M11. There's going to be a 1 here and the rest, and you can think of putting the 1 to M11 out here. So you have a phase function times the reduced matrix. Okay. So if there are no other elements, if everything else is 0 in here, that means that no matter what the light coming in as is going to be, it's going to be unpolarized coming out, and the phase function will determine how much.
Sorry, so is M1 not the beta set?
It is the beta set.
Do you need a Mueller matrix for different wavelengths or
It can be spectral, like a quarter wave plate will be a quarter wave plate, depending on the thickness and the difference in the index refraction. It only works for one wavelength. So it'll be slightly different to go through the spectrum for that. In general, it could be different for different wavelengths. I'm trying to think if anybody has made it's hard enough to make Mueller matrix measurements. I'm trying to think if anybody's done really spectral Mueller matrix measurements. I don't know of anybody who's done that. So there you are. There's a new place to look. Yeah, I can't think of anybody doing that. It's like I say, it's hard enough already.
No. Even in the lab, I know.
Yeah. Yeah. So, we're going to go some instruments for a while. Instruments measure the Stokes factor basically are variations on the radiance instruments. You can have ones that look like Gershon tubes or systems that use a fisheye lens. In general, I told you you need to make 4 measurements to know the whole Stokes factor. Well, in the natural light field, in almost all directions, scattering from aerosols or Rayleigh or reflection from surfaces, typically there's very little circular polarization that comes out in general. So the natural light field, we can usually assume that component is 0. So a lot of times people are only making 3 measurements and determining only the linear polarization parts. It's not completely true that it's equal to 0, but it's pretty close to 0. It shows up it shows up when you have reflections at very large angles from the water to the air interface, and you get the total internal reflection down. You get a little bit of circular polarization in that case. You get a little circular polarization from some animals. They've set up themselves to have circular polarization. And you might get it if you add chlorophyll, it turns out, absorbs one circular polarization more than another. So you might get a little circular polarization, but that would be so small that we can't really measure that. Example of a sky measurement instrument. Here's a fisheye camera system. Basically a fisheye lens. You have some sort of a filter wheel that moves the different polarizers in, so you get a combination of different polarizations. And then the CCD array camera to measure the intensity that comes through the whole system. Here's a picture of a sky instrument on the end of a buoy. Have you heard of FLIP? FLIP's a research platform owned by Scripps, well, owned by Navy probably, but Scripps runs it. It's a long ship, about 100 meters or so. You tow it out to where it's supposed to go, and then they flood half of it, and it flips up like this, so it becomes like a spar buoy that everybody lives on the top of, and it's pretty cramped. But anyway, you live on the top of it up there while you're doing your experiment, and then they put air back in, and it floated like this and come back. So this is an arm-off flip that we have this sky radiance camera sitting at the end. To do in water, there's so much variation in the light field in the water. The sky changes fairly slowly, so you can, within 2 minutes, if you make all your measurements, you probably can combine them and get the Stokes vector. In the water, there's more activity going on, more fluctuations, and so you need to make the measurements simultaneous between the different polarization states. So this is an example of the City College. Where was the City College person? Okay, City College instrument. They have Gaussian tubes set up so they get hyperspectral radiometers, each with a different polarization, measuring different polarization state. You can combine them and then get the Stokes vectors out. The neat thing here is you get very high spectral resolution, okay, because you have hyperspectral radiometers doing it. Same with fisheyes, you can't do the hyperspectral at the same time you're doing the whole imaging part. So it's a multi-spectral instrument. So this just shows three different fisheye systems that all get triggered at the same time. So each of them has a fisheye, each of them has a polarizer in a different orientation. And they get triggered, so you get three different images you can combine with the full Stokes vector. So that's Polarized. Here's another example of a instrument to try to measure the polarization. Once again, it has four fisheye lenses. Behind each of the lens is a polarizer, and then it goes into a coherent fiber bundle, you know, like you do in scope or whatever. And so they come around and they get imaged here through a spectral filter on a camera, so you make sure that all the things, that guarantees everything's going to be simultaneous. So this is another way the instrument that was built to measure the Stokes vector, the light field. There's a brand new system that a student that was here last time was working on with me. There's this really cool camera that Sony makes now. It's about so big. And on each pixel, so here's the photodiode array, basically the camera array, and there's a polarizer set up that's laid on top of here that each pixel has a different polarizer angle on it. And they're set up in groups of 4. And so with those, you get 4 different linear polarization states by looking at the combination of the 4 pixels. And so you get basically one image has all these polarization states. You can use those to determine the Stokes vectors. Okay, they're pretty cool. Here's a picture of the polarizer, effectively. And notice it's got the lines there. Okay, so from what we did before, which way is the light going to get through here? Going to be polarized? It's going to be, light gets through, it's going to be polarized like that. I mean, it's going to absorb that. It's a pretty cool little.
Like FDM.
That's it, yeah, yeah. I mean, these pixels are on the order of 4 or 5 microns. So each of those polarizers is about 4 or 5 microns squared, and they're all lined up on there. So there shows a picture of the image. We're building this to try to help with pace around here. So it's got 3 wavelengths, invisible, which sort of match up with one of the pace polarimeters. And so that's looking down. And then this sort of floats, you can see it floating off the dock. Somewhere, I can't remember where that is. Anyway, it's floating off the dock, yeah.
Is our lens, does it look like that, just all in one direction with the?
It's like that, it's all in one direction, and it's yours is a long chain molecules, so a film. That's not a film, I'm not sure what that is made of. But same idea, yeah.
So when our grading is up and down, wavelengths are going sideways get through?
If the molecule chains are this way or set up that way, then light coming through like this gets through. Light going like this gets absorbed because as the radiation goes through, the electrons in here can absorb it really easily. I said to measure the Mueller matrix. You needed 16 different measurements. One way to do it is by setting up polarizers on both sides and working your way through 16 of them. The first measurement I know of the Mueller matrix was George Beardsley of Oregon State, and that's what he did effectively. Now, doing that takes a lot of time, so you're not sure what your sample's doing during that time. Another way to do it is there's these electro-optic modulators. And you apply an electric field to the electro-optic modulator, and it'll change its index of refraction in one direction relative to the other. And so by having 2 electric-optic modulators that you set up in the right angles, and the polarizer, you can basically sweep through all the polarization states here. And as you look at the output, this has the EOMs and the polarizer. You're sweeping through all the analyzing them all over here. And if you do this, each of these have a different frequency. You look at your signal in your photomultiplier tube, and each Mueller matrix element will come out at a different frequency, some differences in all the other frequencies. So I'm about to retire, and I hope sort of retire in January, fully retire a year from there. Not meaning I don't do any science, but I won't be working at the university necessarily. See if you guys, when you finish, can still show a picture for your dissertation. Okay, 1984, still can show the picture. I guess anybody can show a picture of a dissertation though, right? So not a big deal, but anyway.
But it's the only measurement there from the Earth.
There's some people that have done some measurements in the old way still, or some variation of the old way. But we built this instrument, we used it in the ocean. I'll show you some data from it. It's, I don't know, it's still, I think, one of the best for reference out there. So Mueller matrix for Rayleigh scattering looks basically like this. What this is showing you is this is the scattering angle along here, and then each Mueller matrix element is showing up as so we have the 1, 1 here. It doesn't really show it too well. 1, 1, I've normalized there, so it's just 1 all the way across the top. This axis, each of these graphs goes from 1 to -1 for the Mueller matrix element. All of these for a Rayleigh scattering are 0. So all those off diagonal elements are 0. You have the 1, 2, and the 2, 1 look like each other. They're -1 at 90 degrees, and they go to 0 there, at 0 at 180 degrees. And then you have the 3, 3, and the 4, 4 elements start out at 1, and then go down and become -1 in the back direction for these. Okay? So that's general. We're going to pick out a couple of directions here right now. So we look at Mueller matrix for some specific angles. At 0, the Mueller matrix element had 1s all the way down the middle and 0s everywhere else. What is that in terms of a matrix? Anybody remember what it would be called? That's the identity matrix. Basically, it says that whatever polarization state you come in with, you're going to leave with the same one. Okay, so that's the 0 element. Let's look at this one, 180 degrees. 1, 1, minus 1, minus 1. Okay. What is this minus 1 going to do to your incoming polarization? Just going to, if you have right circularly polarized light, so it comes in with 1, 0, 0, 1, it's going to come out what? 1, 0, 0, minus 1. So it's going to come out left circularly polarized light. So it's going to invert from right to left circular polarization. What's this one going to do? If light was polarized at 45 degrees, that's how you get a hue, say of 1. Then when it comes out, it's going to be minus 1, so it's going to be flipped over like this. Okay. And remember, this direction this way or this way is relative to the propagation direction. So if it comes in like this, okay, polarized in that plane, it's coming looking like that. When it comes back, and you flip it this way, then it basically goes from here to here automatically. So that's why it moves from the 45 degree moves from 1 to minus 1. Because your direction of propagation has changed. Okay, what do these do? We just talked about that. And then sort of the question is why? And Rayleigh scattering is dipole scattering. Okay, small particles considered a dipole. If you have light coming in and it is polarized vertically into your scattering plane. So I'm coming in like this, when I'm coming in like this, I'm going to scatter to you over here. Light polarized like this is, as the electric field is oscillating like this, it's going to excite that dipole to oscillate like this, and you're going to see the oscillation in this direction. Okay, and so there'll be radiation going off because of that oscillating in this direction. Now, if light is polarized in this plane, it comes in, the scattering event comes off this way. Okay, it's come in and made light oscillate, the electrons oscillate in this direction, the dipole oscillate in this direction. But when you look on edge, all right, do you see any oscillation? No, because it's going in and out to you, but no other component, okay? So when you come into Rayleigh scattering, this dipole scattering, if it's oscillating like this, it'll come out really well. If it's oscillating like this, you won't see anything inside. If you look at any other angle, okay, let's go back. I don't have it written generally. Okay. If you look at any other angle, and say you're looking, light coming in like this, you scatter off in that direction, it's polarized in this direction. There is a projection of the light in that plane. And if you think about it, the projection of that is cosine of the scattering angle. Okay? So now that's telling the electric field to get an intensity and get energy out of a wave, you square it, right? So what we're going to get then is you get 1, because for all directions, the part going vertical is 1. But then for the light polarized in this direction, it's going to be cosine squared, right? So if you look at the phase function for unpolarized light coming into a Rayleigh scattering, you have this part, which gives you 1, plus cosine squared of theta, which gives you this other part. So when you look at a phase function for Rayleigh scattering, it's proportional to 1 plus the cosine squared of an angle. Okay, so that's sort of where that comes from in my mind. Right? Kurt probably has a different way. Another thing is, wanted to explain here for a second. is if you look at reflection from a surface, the reflection from the surface varies with which polarization we're talking about. As I said before, light comes off preferentially polarized horizontal to the surface. And this graph is just showing the reflectance as a function of incident angle. And so the blue is the light that's polarized horizontally. The P is the light that's polarized perpendicular to the surface. You notice that at one point the red curve, which is the perpendicular surface, goes to 0 here, and that's Brewster's angle. So at Brewster's angle, when you reflect off the surface, all the light coming off the Brewster's angle is polarized horizontally. There's no vertical light. You can explain that sort of in the same method I just showed you for Rayleigh scattering. So we talked about is unpolarized light coming in like this. When it gets refracted into the surface, at Brewster's angle is the angle where the refracted ray is along the direction of the reflected ray. And so if you're looking down at the surface at that angle, this refracted ray is causing oscillations in directly where you're looking. Okay, so there you're not going to see any, this will only have the component horizontal left. Okay, so remember that, because at the end, and very quickly, I hope we'll bring that up again, Brewster's angle. Okay. I'm going to give a few examples of what polarization looks like in the world. For Rayleigh single scattering, say if the sky was perfectly clear and there was no aerosols, you get Rayleigh scattering. If you look at a hemisphere of information, the solar position's here, so that's like looking right up at the sun. Where you get the maximum polarization, as we saw in those Mueller matrices, would be where one of the components goes to 0. So basically, if 90-degree scattering is where you get maximum polarization. So in skylight, you're going to get maximum polarization at 90 degrees to wherever the sun, 90-degree scattering angle to wherever the sun is. And that's something during this afternoon's, hopefully we'll have it clear enough that you can look outside and check that out. The plane of polarization, preferentially will always be in the plane perpendicular to the scattering plane. And so it ends up being circles around the solar position. And you'll be able to play with that this afternoon. Q and U are hard to understand if you haven't played with it. Even it's still hard to understand, to look at and get much out of. Here's for upwelling light. And the main thing to notice here is there's Q and U, and compare Q and U for sky to Q and U for upwelling light in clear water. It's very similar type pattern between the two things. Mueller matrix for ocean water. So this is the general one. The paper had Atlantic, Pacific, and then Gulf of Mexico, and then all combined. And so this is all combined, I'm pretty sure. What you notice is that the off-diagonal elements are 0, just like Rayleigh scattering. Notice the 1, 2, and 2, 1 element, they're the same, but they don't go all the way to -1. So what does that tell you about water scattering? If it went to -1, what happens there? So if it goes to -1 here, then it means that if you have unpolarized light coming in, it'll be fully polarized at 90 degrees. Okay, because you have, if this is -1, you'd have 1 times 1. Oh, I'm sorry, this element, you'd have 1 times -1. Well, if you come on in, yeah, so you have to have 1 -1, 0, 0. If you come in 1 times -1 plus the next element -1 times this one, say for Rayleigh scattering is 1, then you would end up with -2, but there's a half in there. So it'll go away. If it's -1, it ends up being fully polarized. By not being quite -1, it's not fully polarized. All right. So you have this. These elements don't go quite back to -1 like you do with Rayleigh scattering. So you're not getting the total polarization there. This 2-2 element for radiant scattering is 1. The fact that it's not 1 here is probably the biggest indication that we're getting some scattering from non-spherical particles. When you get non-spherical particles, it shows up as a 2-2 element. It's not. Okay, but that's the example. The general form looks a lot like Rayleigh scattering.
So Ken, these can also be used to determine whether the particles are randomly oriented or not in the water.
Yeah, yeah. Some of the off-diagonal elements will show up when they're non-random oriented. But these, well, and to be fair, who knows what they would be doing in the water, because the way this instrument had to work was on the deck, trying to take samples and put it in there. So I don't know what they were doing in the water. This is what they were doing in my scattering chamber. Okay.
Why aren't we seeing a reading all the way to 180 degrees?
Because if you build a scattering instrument, it's really hard to make the measurements back in that direction. If you remember what the phase function looks like, it's very sharply peaked in the forward direction, falls off. So what ends up happening is if you have any scattering chamber inside your lab, is preferentially forward scattered, probably reflected off something inside there, and then that's what you would see when you look at back, not backward scattering. So instrument limitation. We don't have data back. I didn't have data back here. Actually, it doesn't go all the way to 0 either in the forward direction, and it was only plus or minus about a 0.05. So to get more accurately, chlorophyll dichroism might show up in these 2 elements, but I couldn't do it.
But you were saying that it's partially polarized, not the water will absorb like it's horizontal, like mostly horizontally polarized, and some of it going in a different direction, or just like.
So that means if you sent in unpolarized light, say into the ocean, it doesn't get fully polarized in any direction. If you send unpolarized light into a perfect Rayleigh type atmosphere or medium, at 90 degrees it'd be fully polarized in the direction perpendicular to the scattering plane. With this, if you send unpolarized light into the ocean, it's not going to be fully polarized in that direction. It's going to be partially polarized. You can think of partially polarized as having an unpolarized component plus a polarized component added together. Okay. That makes sense or not sense?
Yeah.
Close enough. Okay, where are we here? Yeah, this is just to show you the difference between the two again. So why do you care? Use of polarized light for enhanced imaging. Scattered light is more polarized than light reflecting from a surface. Most of the time, light reflecting from a surface gets depolarized. And so you can separate the light being scattered by the medium in between you and the target from the light being scattered from the target. I think the first paper I remember seeing about it was Gary Gilbert in 1967, yet as you read applied optics, about every other year someone rediscovers it and it comes out again. Animals, polarized detection by animals and polarized light camouflage. There's been a bunch of experiments done for that. Molly Cummins and Roger Hanlon, Molly's at UT, Roger Hanlon at Woods Hole Marine Biological Lab. There was a big Navy project that they did a bunch of work looking at that. Minerals, depolarized. Remote sensing. This is for Mueller matrix elements from silt, and the F. Remember what it looked like in my measurements for 1, 2. It basically started out at 0 and went to -1 and back up. Here you see something completely. Well, this is minus, so we go here and up like that. Here you can see something completely different. So maybe very hard particles will, definitely hard particles, high index particles will have a different kind of Mueller matrix than, and you might be able to tell something about the particles there. The guys at City College have the idea of measuring the degree of linear polarization, and there's a relationship between the degree of polarization and the beam attenuation divided by absorption. The higher the beam attenuation relative to the absorption, the more depolarizing effectively things get. Mostly it's a multiple scattering effect. As you have multiple scattering, every time you do a scattering event, basically if I have light coming in like this, I scatter over there, I could find a scattering plane that's relative to here. Say that was too easy. Come in here, go up there, scattering plane looks like this, it now gets scattered like that. The new scattering plane is like that, so the scattering planes are all mixed up. And the polarization, then it destroys the degree of polarization. Your instrument could have polarization sensitivity. Some of the spectrometers people started using for above water radiometry were polarization sensitive, and so that can screw up what you think you're measuring in terms of the intensity of the light. It might give a different response for one polarization state versus the other. The ocean color satellites we're using are polarized. They try to be unpolarized. Well, the normal ocean color ones, say Veers and Modus and such, try to have unpolarized measurements, but there's always a degree of still polarization sensitivity. And so that leaks through. And so when you look at a measurement of the water, you need to correct for this polarization. Especially what's really important is the atmosphere. The atmosphere is highly polarized relative to the ocean. And so you really have to take an effect looking at the atmospheric correction. It fits in. There was an idea they would put a polarizer on Glory. Unfortunately, Glory didn't make launch, it crashed in the ocean. But there's supposed to be 2 on PACE polarimeters. They're really important for atmospheric aerosols, and people are exploring what you can get out of it for the ocean. Here's a little discussion topic. I was trying to I looked through the PACE mission science team document. I think you probably wrote it or a part of it. And I was trying to find the newest articles on polarization so I could do it. And I just happened to look at this image and read the explanation. I thought, I wonder how much they thought about this. So here's the degree of linear polarization versus wavelength for blue, green, and red. The brown curve is how you see do it on water. Okay. Now these are measurements. They don't describe a lot about it. They're made in the Keys or Florida Bay. They were all done near Brewster's angle. Okay. So think that. What do you know about Brewster's angle? All the light coming up is polarized. All is polarized like this, okay? So if it was just the light reflecting off the surface, what would you expect the degree of polarization to be? Basically 1, fully polarized, all right? So now let's think about blue light. I'm looking at the surface in blue light in an ocean's blue. So I get a lot of light coming up from the water that's, okay? By the way, they made no correction for the surface in this. This is all above water looking. So there's going to be a lot of blue light coming up. So relative in blue water, if I say that the ocean is totally unpolarized, and I look, I'm going to decrease the degree of polarization tremendously in the blue, and then as I go toward the red, there's going to be less light, and so you're going to see more of the surface. Okay, so now I'm going to have a higher degree of polarization, just because the blue, the signal from in the water, even assuming it's unpolarized. and the signal from out of water. So that explains the blue. How about the brown curve, the high CDOM curve? Does it explain that? This idea that we have? If you have high CDOM, do you have much light coming out of the blue? No. So almost everything's going to be in the surface. So you're going to see mostly this reflectance off the surface. Okay. And so you get a high degree of polarization.
Inverse reflectance.
What's that?
These curves look like inverse reflectance.
Yeah, yeah. So basically, you're measuring the mixture between what you're seeing from this in the water versus what you're seeing from the surface. It's not really telling you anything about what's going on in the water in terms of polarization. Okay, so, and I'm sure there was an idea about above water radiometry that Robert Cohen put forward, and the idea of using Brewster's angle or using polarization by saying that all the light's going to be polarized like this, so I'm just going to look with a polarizer this direction when we get the subsurface. So people talk about, okay, above water, use Brewster's angle. But in terms of measuring your degree of polarization, it's a really bad idea because you're starting with a fully polarized signal there, and what you're really doing is just measuring how much the surface is affecting your signal versus in the water, not what's going on in the water. Okay. So so that was. What's that?
Pass the comments.
Yeah, I read that. Oh no, really? Anyway, any other questions? I'm done.
I'll just make a comment following up on what you just said. So I was in Brazil one time, and they had made all of these measurements of remote sensing reflectances in all of these lakes and stuff around Brazil. So, you know, what you need to know is ED and LW, and you can get RRS. But then there's this problem of removing the glint. So they thought, oh, well, when we point our radiometer to the surface, we put a polarizing filter on there, we'll remove the glint. And they get these LW numbers. The problem is they didn't even realize that if you pass unpolarized light through a linear polarizer, you only get half of the irradiance coming out because you're going to lose half of it blocking out the polarization. Well, when they point the instrument at the water and they put the polarizer there, at best you get half of the light coming through, but you really get less than half because of whatever the polarization state happens to be. So what they had done is they'd gotten a decent ED measurement, and they had totally messed up their LW measurement by using a polarizer. And the end of the result was they had to throw out all their data from innumerable field experiments because you didn't know for the particular lighting they had what the polarizing filter was actually doing to the reflected light. And it looks good, you look at it and you say, oh, there's this dark spot on the water, I blocked all the skylight. Well, that's true, but you've also blocked an unknown amount of the water leaving radiance, depending on what its polarization was. So it was a real fiasco. And, you know, I felt bad for them. I had to tell them, sorry, the reason your RRS's values look weird is because your LW values are just like off by factors of 2 or more.
And the polarizers themselves are never perfect. So there's a loss of transmission, spectral transmission.
Yeah. So this afternoon's lab basically starts at 1. It's just all qualitative. And it should be on the website now, maybe. We just finished it this morning, so it's on the website, the description. Basically, you're gonna at least have 2 people, so you get 2 polarizers in the group.
There's 2 people polarizing.
You hand it out.
I know where I can find it.
Okay, well, still, it's good working with with 2 people. So you got 2 people. It's basically getting you a feel for polarization, both polarization during a scattering process by sort of repeating some of the stuff you did in the light, playing with the light the first day. And then also, since it is fairly clear today, to go out and look at the sky and then also look at the water surface with the polarizer and look to see where the polarization is maximum or minimum, or where the plane of polarization is and things like that. So there's no write-up for tomorrow for this. You can redo some of the radiometry stuff for tomorrow. And anything else important about that? There is something, but I can't remember. If you looked at remember the plane of, the degree of polarization for the skylight is highest at 90 degrees scattering angle, okay? So yesterday I noticed from the microtops measurements and looking where the sun was, basically the sun was pretty high here at 1 still, okay? So perhaps the best idea is to keep the polarizers until tomorrow. And then you can look at the sky now, but the highest polarization is going to be near the horizon. The problem with that is the horizon is also where you get brightening because of multiple scattering in the atmosphere. So you probably have a less polarization there. If you look later in the day when the sun gets lower, the 90-degree scattering angle is going to be higher in the sky and you'll get to be able to see it better. So look during the lab time, but also keep it, and if it doesn't do the normal main thunderstorms in the evening, it's not supposed to, I think. Use the polarizer again and go out later. When you have your beer, go out and look at the same time. It's amazing how much optics you can do with beer. Anything else? Yeah, I used to, Scripps, anybody from Scripps? Okay. Scripps, they used to have the teaching. They'd have it at the, where they built, I think they built a convention center now, there used to be a hut there.
There's still a hut and there's still teaching in the hut.
Okay, cool. By the water?
Yeah.
Yeah, okay, so, I don't know, I've been a postdoc there, I don't know how many days on Fridays we go down and how many green flashes I saw. Hanging out of the water, you got beer, you look out at sunset. I saw amazing numbers of them. Anything else? Okay, have fun.
I have another question.
Yeah, sure.
Okay, so in order for things to be polarized, some amount of light has to be absorbed because, yes, no, because there's that fractional.
Yeah, well, you can also polarize light by reflection. Okay, like we did at Brewster's angle.
Yeah.
All the light comes off, it's going to be polarized in this direction.
Okay, so like it's the same intensity gap, but just at a different.
No, they actually are much less, because a lot of that Brewster's angle, a lot of it went into the material. So you're saying, how can I make?
Well, because I was thinking like where you have all the like the diagrams of a particle, you have light that's like diffracted, you have light that's absorbed, and light that like goes into the particle and is scattered back. Which parts of those are affected by polarization?
The diffracted part isn't.
Yeah,
That's always very, very near
Yeah.
forward, and pretty much it has a Mueller matrix of 1.
Yeah.
Okay. All the other directions are going to have a Mueller matrix associated with them that will change the polarization.
Okay.
The
Because like when if you were shining light and you polarize like at 90 degrees, half of it, like what happened to the other half of the light that's supposed to go the other way? Does it just shoot off in a different direction? Because I guess it depends on the angle that you look at it.
Yeah, so